Okay, my name is Donghyun Shin. It's a South Korean name. So we have, the several faculty members from South Korea. I mean, I think you met Hans Jung, right? Yeah, he's also one of my friends. Hey, my office is Engineering Technology Building in room 234 on the corner right there. This is my phone number. I never used in the last 5 years. And this is my email. So if you want to contact me, this is the best way. It's not like, the long time ago, we have a smartphone, when you send an email, we can check right away, even though you get response hours later, right? And my office hour is Tuesday, Thursday from 10:45 to 11:30 in my office. Or if you don't want to see me, you can send me an email that I don't want to see you, but can you log on WebEx? And I can do that. The WebEx link is available on Blackboard. So if you go to Blackboard, you can find all the information, okay? If you have a scheduling conflict, if you have a conflict this time, you can send me an email to schedule another time, which is totally fine. I'm in place of the class meetings. I think you all know because you are here. Oh, 128. I don't know why there's a question mark. 128. We are very lucky to be in this room because if you go the other side, it's really hot. I just finished, the Thermodynamics 2 and heat transfer course. That's the seniors course. There were 25 students. Without the air conditioning is running, but there's no, the cold air. It's hot and humid. If you go down, you can see the textbook. I think you have a lot of questions about this textbook, Fundamentals of Engineering Thermodynamics, 9th edition. I think you got an email from the library about the all-inclusive access. You can use it. If you don't want, you can cancel it. We're not going to use that all-inclusive, the programs. I just heard that it's cheaper than buying a hard copy, so I requested it. If you don't like it, you can buy a hard copy elsewhere, which is totally fine. Another question may be, can I use older edition, previous edition, 8th, 7th, which is cheaper? No problem. You can do that, but you need to find a rich friend who has the latest edition because the homework assignments is based on the latest edition. I don't have all the previous editions and then find all the homework assignments, find the match, this. I cannot do that. So if as long as you have a friend who has the latest edition, you can use the older edition, which is totally fine. Okay. But I recommend you have a hard copy because the thermodynamics you will use it. I'm for sure when you go to career because we in this course we deal with energy. When you go to engineering application, it's all about energy. There will be 3 tests, 30% each. So that means that we have 2 midterm exams and 1 final exam. And the final exam is not comprehensive. Okay, so we are going to study 8 or 9 chapters. We are going to evenly, divide into 3. So you will, take the first exam that covers the first, the 3 chapters. Second exam, the second 3 chapters. The last exam is going to cover, the last 3 chapters or 2. Okay. Each test, each exam has 3 or 4 problems, generally 4 problems, because I assume that in my opinion, it takes about 15 minutes at the max to solve a thermodynamics problems. So if I give you 4 problems, technically you need 60 minutes to solve it. So each exam is going to be 1 hour. You will see 3 or 4 problems, that including the final exam. The final exam is 1 hour. You will see 4 problems. In the previous, the years, there were students asking, this question, the other class, the courses, they have a 2-hour final exam. Can I get 2-hour exam? Yes, I can give you 2-hour exam, but you need to, meet your friends and then make sure that everyone agrees. So if you want 2-hour exam, just let me know a week, the advance before the final exam, so I can prepare a new exam sheet that has 4. So each problem takes about 15 minutes. So if you want 2-hour exam, I can prepare, the 8 problems. If you want 3-hour exams, I can prepare 12 problems, whichever you want. If you want, the 2-day exams, like 48 hours, and I can multiply by 4 and then present those exams for you. So, but what I learned from my 10 years of teaching this course in the last, everyone liked, the 1-hour exam. Okay. Which is, which makes sense because the final exam is not comprehensive. Why you need the 2-hour exam, right? Homework assignment is 7%. I'm not going to accept any hard copy. Let's save trees, okay? So what you're gonna do is that write down, on a scratch paper or Microsoft Word or something, you don't have to write down any problem statement. Just write your solution clearly so I can understand, how you, whether you did read right or you messed up. If you didn't get the right answer, what is the problem in the solution. So you need to write solution clearly. So if there's a partial credit is given, so I can give you partial credit. If you don't write any solution and your final answer is wrong, how can I give you partial credit, right? But you don't have to write anything, about the problem statements. It's a waste of time. Just write it somewhere and then take a photocopy on your phone or something, convert into a PDF. You know how to convert JPG or PNG files into PDF, right? Or if you don't, to go to a website called ilovepdf.com or something. They have a pretty nice, everything for free. Or you can go to Microsoft Word and copy your JPG file and then paste on your Microsoft Word and then print as a PDF. Okay? Just to make sure that you compress PDF enough. Don't upload, the 1 gigabyte PDF that takes about 20 minutes to download. There's one student last semester. He usually upload like a 1 gigabyte PDF. So I have to wait in my, computer to, to pull up this, download everything. Okay. If you don't know how to compress PDF, you can also go to ilovepdf.com. They have a free, it's free to compress your PDF. Attendance is 3%. I'm not going to check attendance every class. It's a waste of time, but I will do 1 or 2 times. When I see the lowest attendance, so that's going to be, in my opinion, I call it judgment day. So I will check attendance 1 or 2 times. That will be 3%. So my recommendation is that don't miss any class. Sometimes, when you review, each course, after, the class is over, you need a help or something, to help that, I'm going to record all the lectures and then post on the Blackboard. But it takes time because I need to, the process, the video. I don't want to upload, the 30 gigabytes, the video on Blackboard. It takes, the hours. So I need to process, everything. It takes about days. So I usually upload lecture recordings during the weekend. So if you wait, and you can see them. That doesn't mean that you don't have to come to the classroom. Remember that 30% attendance is going to be pretty, the big number, okay? Late assignments will be accepted anytime before the final exam. So if you miss the deadline, don't send me an email that can I, submit late. You can submit late as long as the day is before the final exam, okay? But there will be 20% penalty because, it's not fair if I give a full credit. There are, the students who submit on time, but 20% is not that big numbers. Consider that there are 7 homework assignments in this course. So each homework assignment is 1% of your final grade, and 20% of 1% is going to be what? 0.2%. So if you miss the deadline, you can still submit. Remember, you can still submit, but don't complain about the penalty. It's pretty small, okay? But submit homework, don't lose that 1%. 1% can change the grade, right? So that's pretty much everything about this course. Any question? No? Come again? Oh, it depends. Let's see. Let's go to the Blackboard. together. Oh. By the way, feel free to interrupt any time during the class. Everyone talk about active learning. I don't want to be, the alone talking, in the classroom. Don't assume that you are the only one have that question. I'm pretty sure that, if you have a question, your friends also have the same question. So ask anytime. Last year, I got 5.5 out of 5 from this IET 356. So if you participate, that class has a great participation. So if you go here, oh, you cannot see me? Oh, this one. If you go here, you can download the syllabus and course PowerPoint. By the way, I don't read your textbook from page 1 to page 1026 or something. It takes time. It takes a lot of time. You don't want to just read a book for the entire semester. I made very nicely done, in my opinion, the summary for each chapter. Start with the PowerPoint, okay? It has, all the practice problems, so you can, solve those problems first by learning through this PowerPoint slide, and then, go to homework assignments and solve them. The best way to, study engineering and technology is solve as many problems as you can. I'm a living example. 4.5, everything. Okay, so try to solve as many problems as you can. Like when you get up in the morning, try to solve some problems. When you're cleaning your toothpastes, so try to solve some problems. When you're eating something, try to solve some problems. And then now you need to practice how to eat with your left hand or something, right? Then while you're coming to the classroom, do not try to solve a problem, right? You need to concentrate on your driving. But when you park your car in the parking lot, you can solve some problems on your windshield, right? When you go to the restroom, try to solve some problems, okay? If you keep doing that, and if you don't get, the A, then you can submit a complaint. If you keep solving problems, I guarantee you, you will get an A. Because, in engineering technology, there is not many things that I can do. When I design a problem in chapter 1, those problems that I design, it's not going to be far different from the problems in your homework assignments or the PowerPoint problem. So if you know how to solve them, you already practiced enough. Any small variation, there will be no problem. Okay. And if you keep going down, there's by the way, this one, property tables. Majority of our problems, they require you to use these property tables because that's the, the how you study thermodynamics. So print this one, but do not print it from page 1 to page 96. It has 2 sets. The first 48 pages are SI units. The next 48 pages are the same table in English unit. Okay, you can just print the first 48 pages. Because in our class, we are going to use SI unit in the classroom. We are going to use only SI unit in your exams. You will see some English units in your homework assignments. So that you get used to the converting the SI and English when you have plenty of time, homework, but not in exam, limited time. Okay. And if you go to homework, if you click it, you can see the number of homeworks. Okay. If you go to your textbook, there are 3 different, the exercise problems. Make sure that you solve the problems under this heading, developing engineering skills, right? There are another set of problems, the OX, the quiz or something. Do not solve them, okay? Only the problems under this one, okay? Any question? Any question about thermodynamics? Any question about CMU? Any question about our department? Any question about me? I need to introduce myself, right? You search my name, you can find me. This is the research website. So what I do is that, I synthesize nanomaterials to use it in a solar power plant. So something like that. So I design, the material to be used for thermal energy storage. So we can store energy when we produce electricity in the daytime, and we use that energy in the nighttime. So even though there's no sun, we can provide electricity 24/7. Some of you can say that, we have a battery system. If you buy a Tesla, there's a battery inside. The problem of that battery is that, it's too expensive. If you buy a Tesla, about 40% of the cost is going to be in the battery system. And this is a thermal energy storage. So we don't store energy in the electricity form. We store energy in the form of heat. And then we use a Rankine cycle to produce electricity later time in the day, in the nighttime. The good thing about, the thermal energy storage is that it's pretty cheap. You don't use any, the real materials on the earth, like a lithium or something. So the price is very cheap, and then you don't need to replace every 4 hours, every 4 years. So you can use it for several decades. The problem is going to be you cannot use this thermal energy storage for your vehicle. You need to be a certain size to maintain a high temperature. Oh, by the way, this is a solar thermal power plants installed in Nevada. So it produces electricity. It was built by Google. It produces electricity. That electricity is going to be used in nearby big city called Las Vegas. So this is the electricity they run all the, the machines over there. Okay. So that's what I do. Five years straight, 2% in the world. Number 9 in solar thermal in the world. Anyway, so that's everything about me. If you have a question about my research or anything, just you can send me an email. Let's get back to thermodynamics. By the way, we are going to study 9 chapters. And just for your heads up, the first 2 chapters are not very interesting. So be patient until we finish first 2 chapters. Imagine that you want to play a video game. Like, let's assume that you just bought a PlayStation. And you just turn it on. And it's going to be fun right away. No, you need to know how to play that game. Let's assume that you want to play something like, the fighting game between 2. You need to know what this button A means. You need to know what this button B means, and C, D, E, F, etc. And these days, they're not just 2 or 3 buttons. There are 200 buttons there, right? So you need to know, if I press button number 1, it's going to be a punch. Next one, button B is going to be jump and kick, etc. Once you know how to play a game, now the game is going to be fun, right? It's like in playing sports too. If you don't know any rules about baseball, it's going to be fun? No way. You need to know about that. So first 2 chapters, chapter 1 and chapter 2 is about, the how to play thermodynamics. Okay. So until you mastered chapter 1 and 2, It's not going to be that exciting, so please be patient if you are not very happy with the first two chapters. Right? It's going to be boring. I warn you, okay? So let's talk about the first slide. This one here. So this slide has every law, every scientific law we are going to use in thermodynamics. There are only two of them. The first law, what's the other one? The second law. The first law is about conservation of energy principle. Everyone has a pretty good idea about conservation of energy principle, but it is always easy to understand a law if you have a good example. Let's assume that, in the morning today, that I was very hungry. So I ate, the 5 hamburgers in McDonald's. Oh, that's too much. So in the afternoon, I pooped out 3 hamburgers in the restroom. How many hamburgers in my stomach? 2. That's the conservation of energy principle. Pretty simple, right? So if you look at this example on the right-hand side, this one, there is a rock on top of this cliff. And let's assume that the potential energy is 10 units. The potential energy is the energy associated with gravity. So if you climb up the Mountain Everest, that means that your potential energy goes up. If you jump down, do not jump, but if you do, the potential energy goes down. If you go to the second floor, imagine that, your potential energy goes up. If you go to the first floor, if you, come down to the first floor, the potential energy goes down. So when the rock, the falls to the ground, the potential energy is going to be converted to kinetic energy. This PE is potential energy. KE is kinetic energy. Kinetic energy is the energy associated with velocity. The higher the velocity, the higher the kinetic energy. So when velocity goes up, kinetic energy goes up. So while the rock is coming down, the potential energy is going to convert it to kinetic energy. And as you can see from here, the sum of these energies, 10 units of potential energy and 0 units of kinetic energy, because it was stationary. Once it starts to move, the potential energy comes down and kinetic energy goes up. The sum of potential energy and kinetic energy is 10. So that shows conservation of energy principle. Is that right, or there's something wrong? Is that right? Technically, there is something wrong. What is that? If this happens in space, this one is right. However, on the Earth, what happens? There's air. So when rock is, falling down, due to the friction between air and the surface of this rock, there is heat is generated. Heat is a form of energy, thermal energy. As we know, energy cannot be created or destroyed. That heat should be from somewhere. That is kinetic energy. So in reality, it's not 7 plus 3. It's going to be 7 plus 2.999 something plus a small amount of heat, 0.001 or something. Then it becomes 10 units altogether. Make sense? Then once this rock hits the ground, what is the potential energy? 0. So potential energy is going to be 0. And what is the kinetic energy? 10. So once it hit the ground, now we're going fast this way. That's not the case, right? What is the kinetic energy of the rock once it hits the ground? 0. That's right, 0. So what is the sum of potential energy and kinetic energy? 0. So what's wrong with this conservation of energy principle? Now we just violated the first law. Am I right, or there's more explanation? So once the rock hits the ground, the rock is not going to be okay. It's going to be, divided into, the smaller pieces. That means chemical energy has been entered the rock. So there is a change in chemical energy for the amount of almost 10 units. So the leftover is going to be chemical energy plus thermal energy, which is heat. So once the rock hits the ground, the temperature of the rock goes out slightly, and the breakage of the chemical bonding between atom to atom, that is the total of the the chemical energy is going to be approximately 10 units. So this example does not violate the first law of thermodynamics. Throughout this semester, we are going to solve many thermodynamics problems, and then all the governing equations. Most of the governing equations in these problems are based on conservation of energy principle. We are going to use that governing equation. We are going to study that governing equation when we go to chapter 2. Okay. So chapter 1 is more like the background information for you to to play a video game. So if you want to play a video game, what do you need to know? How the button A means, button B means? No, before that you need to understand electricity. You need to plug in, then this one works. So chapter 1 is like that bottom level. So how science works. Then when we go to chapter 2, we are going to study how what is the background for thermodynamics. So like governing equations and etc. What is heat? What is work? Those are the things that we are going to study in chapter 2. So once you complete the science background, chapter 1, thermodynamics background, chapter 2, then you can study thermodynamics from chapter 3. Okay? That means that we still have a little more the boring parts in chapter 1, right? So the second one is going to be the second law of thermodynamics. We all know from our experience about this second law of thermodynamics. What is it? Heat flows in the direction of decreasing temperature. That means if you have a hot coffee, I don't have a coffee, I drank already one in the morning, so let's assume that this is coffee. The color looks pretty similar, right? So let's assume that this is a hot coffee. What happens if I place this hot coffee on this table? Now, there's a heat transfer from the coffee to the surroundings. So the temperature of the coffee goes down, the temperature of air goes up. Why is that? Because heat flows in the direction of decreasing temperature. In other words, it flows from a higher temperature point to a lower temperature point. So if I have a hot coffee here and then put in here, what happens is that its temperature goes down. If you have a hot coffee, if you grab it and you feel that it is hot. Why you feel that it is hot? Because there's a heat transfer from the coffee to the cup to your skin. So when you receive that heat, then you feel that it is hot. When you hold on ice, you feel that it is cold. Why you feel that it is cold? Because there's a heat transfer from your skin to the ice. Then when you the holding a high temperature, a cup, hot cup or something, sometimes you just feel that, oh, it's hot. Sometimes you feel that, oh, sometimes you get burned. And what condition you get burned and what condition you just feel that hot? When the heat transfer, the amount of heat transfer is significantly high, then your skin cannot withstand that large amount of energy transfer. Then you get burned. Because once your heat transfer through to your hand, that heat needs to go away due to the conservation of energy principle. Energy cannot be created or destroyed. Once you touch this high temperature cup, that energy, that heat, goes to your skin, need to go somewhere, otherwise you get burned. If the amount of heat transfer is too high, the speed of the heat transfer through your body cell is less than the amount of heat, then you get burned. Okay? Imagine that there's a swimming pool in the student activity center. Have you been there? There's a pool, and there are some rooms. What are those rooms? Yeah. Imagine that, what is the temperature inside the sauna? Pretty hot, right? So usually the temperature inside the sauna, I don't know about this stack, but if you go to the other the general commercial areas, the sauna, if you go into the sauna room, the temperature of the air inside the sauna is above the temperature of the boiling temperature of water. And now let's do something interesting. Let's imagine something. So now sometimes that you feel that the water in the swimming pool is too cold. So you turn on the heater. And the next day you come back to the swimming pool, you see water is boiling. Can you jump into the swimming pool? You can. Just one time in your life, right? You can jump into the swimming pool and then that's over, right? But if you go to the sauna room, even though the temperature of the air inside the sauna is higher than the temperature of water in the swimming pool, you don't die. You stay there about 10 minutes and then comes out like an Iron Man or something. You survive. Why is it possible? Even though the temperature of the air inside the sauna is higher than the temperature of water, the amount of heat transfer from water is higher than the amount of heat transfer from air. That makes sense? So it's not about temperature. It's about the amount of heat transfer. That's what we study in thermodynamics. So I guess that you have a pretty good knowledge about the first and the second laws. Let's continue. Dimensions and units. I'm pretty sure that you have some knowledge about what is dimensions and units. Of course, you have a pretty good idea about units. There are 2 units, SI units and English units, right? Then what about dimensions? There are primary dimensions and secondary dimensions. Primary dimensions are those that cannot be divided into 2, like distance. Let's say from here to the door is 5 yards or 5 meters. Can you divide into 2? No, it's just the distance. Can you divide distance into 2? No. But what about velocity? How you determine a velocity? Velocity is distance divided by time, right? So velocity becomes 2, distance over time. What about acceleration? Distance over time, right? Distance over time square. So those that you can divide into the different dimensions are called secondary dimensions. Those you cannot divide are primary dimensions. So in thermodynamics, among many dimensions, we are going to use only 4 primary dimensions. They are mass, length, time, and temperature. So any dimensions that we study in thermodynamics, they're going to be a combination of these 4 primary dimensions, like velocity, energy, force, etc. Then why do we need to know about primary dimensions or secondary dimensions? One of the benefits of using, knowing primary dimensions and secondary dimensions are dimensional homogeneity. So when you have a governing equation, when you solve it, the dimensions on the left-hand side of the equation should be the same as the dimensions on the right-hand side of the equation. So you can use this dimensional homogeneity to verify your calculation is okay or not. So we will, study dimensional homogeneity later when we solve some example problems in the PowerPoint. Okay, maybe in chapter 2. Okay. By the way, if you have a question in the middle, please feel free to interrupt. Okay. Then let's talk about systems and control volumes. Systems is a quantity of matter or a region in space chosen for study. So, for example, if you want to study, how heat transfer occurs from this high temperature coffee. It's not a coffee, but I don't have a coffee here, so let's assume that this one is coffee. So this coffee is at high temperature. So the coffee is at high temperature in SI unit. What is the boiling temperature of water? The boiling temperature of water is 212 Fahrenheit. In SI unit, 100 degrees Celsius, right? In real life, yes. In thermodynamics, no, but we are going to talk about that later in chapter 3. So the boiling temperature of water in general is 100 degrees Celsius. Let's assume that the coffee is not boiling, below slightly, the lower temperature than the boiling temperature. So let's assume 90 degrees Celsius. And the surrounding air is going to be 20 degrees Celsius. Then due to the second law of thermodynamics, heat transfers from a higher temperature to a lower temperature point. So we expect that there is a heat transfer in this way. So there's a heat transfer from the coffee to the surroundings. So if you want to study this heat transfer, we need to determine its system, a quantity of matter or a region in space chosen for study. That system is going to be the coffee. So in this case, the coffee is the system. Then what happens? There's a heat transfer from this coffee to the surrounding air. Then what is the surroundings? The surrounding is going to be this air. So here we have system, and here we have its surrounding. The mass or region outside the system. Then what about this cup? Cup is the boundary, the real or imaginary surface that separates the system from its surroundings. So this cup is going to be its boundary. So what we usually study in thermodynamics is the energy transfer between a system and its surroundings crossing its boundary. That is a typical thermodynamics problems. So depending on the energy transfer that you want to investigate, you need to select the right the system and surroundings. So designing thermodynamic problem is one of the key for success in this course. Okay. And then this boundary can be either real boundary or imaginary boundary. What is the difference between real and imaginary boundary? Real boundary means the cup itself. So there's a coffee inside, and this coffee cannot cross this boundary. That is real boundary. So real boundary means only energy can transfer. If you're holding a hot coffee, then you feel that it is hot. That means energy is transferring from the coffee across this boundary, which is a cup, and then go to the surrounding, which is your hand. So real boundary, energy can transfer, but mass cannot transfer. Imaginary boundary is going to be here, the opening. If you don't have a lid, this one is imaginary boundary. So imaginary boundary means that mass can transfer. If I do that, the coffee can, comes out. So that's an imaginary boundary. Mass and energy can transfer. So anything can transfer is imaginary boundary. Only energy can transfer is the real boundary. Okay. So once you know, so the first part, system, surrounding, boundary, this is about how you design a thermodynamics problem. Once you design a thermodynamics problem, there are two ways to study this thermodynamics problem. One is a closed system. The other one is an open system. Closed system means there's no mass transfer between a system and its surroundings. So if I have a coffee and close the lid, then it's going to be a closed system. Whether it is hot or cold, energy can transfer, but the mass coffee is not. That's a closed system. On the other hand, open system means then it's going to be open system when there's a mass transfer. We have an air conditioning system right here. There's air coming out. So you want to, analyze this air conditioning system thermodynamically, then what is going to be your system? Yeah, it's going to be open system, but what is going to be the system of your thermodynamic problem? The system is going to be air. Boundary is going to be the device. And the surrounding is going to be whatever the fluid inside the air conditioning system, that's going to be refrigerant. So you can study the energy transfer between refrigerant and air circulating in that air handler. So that can be one thermodynamics problem. In that case, air is coming out and then goes in. So you can consider the air conditioning system as an open system. So the governing equation, even though we apply the same law, conservation of energy principle, the governing equation looks slightly different between a closed system and an open system. So we have two different chapters, one for a closed system, the other one for an open system. Closed system is going to be chapter 3. Open system is going to be chapter 4. Then let's talk about an example. Previously, I told you that the first law is conservation of energy principle, and the second law is the direction of heat transfer. So if you have a hot coffee, so you have a cup and there's a hot coffee inside, 90 degrees Celsius. There is air outside, 20 degrees Celsius. Then you expect the direction of heat transfer is going to be from here to here. So this is the direction of heat transfer based on the second law of thermodynamics. Am I right? Yeah. Now, if you hold this coffee cup, of course, it's going to be hot. 90 degrees Celsius is way above your body temperature. What is your body temperature? 36.5. Sometimes you can be 38 or 39 if you have a fever or something. So then, when you grab this hot coffee cup, the coffee is 90 degrees Celsius. Then what is the temperature of the cup? 90 degrees Celsius, or greater than 90 degrees Celsius, or less than 90 degrees Celsius? It should be less than 90 degrees Celsius. What about if the cup is also at 90 degrees Celsius? Okay, so the coffee is 90 degrees Celsius, if I assume that the cup is also 90 degrees Celsius, is it possible or not? Possible? Oh, okay, it is possible. So now you are going to hold this cup. So these are fingers, index finger, middle finger, and what is the next one? Huh? Okay, ring, and then, and no, there's no more than, right? So if you hold it, I'm going to assume that the coffee is 90 degrees Celsius and cup is 90 degrees Celsius. Can you hold it? No, because it's too hot. No, it's not too hot. If you assume the coffee is 90 degrees Celsius and cup is also 90 degrees Celsius, what is the direction of heat transfer? Due to the second law of thermodynamics, heat transfers from a higher temperature point to a lower temperature point. And the coffee is 90 degrees Celsius. Cup is 90 degrees Celsius. What is the direction of heat transfer? There's no heat transfer. So when you grab a coffee, it shouldn't be hot. So if the cup is the same temperature as the coffee, that doesn't make sense. You see the problem? So to make a heat transfer from the coffee to the outside, the cup temperature should be less than the coffee. Otherwise, there's no heat transfer due to the second law. Interesting, right? Then let's talk about one more interesting example. What about I'm going to buy a refrigerator like that, and so this is a refrigerator. Is this the refrigerator you want to buy? Oh, of course not. You know, the good ones have more doors, like the two of them on top and two of them at the bottom, and there's a meters, there's a LED screens, and everything, right? No. So then, when the refrigerator is working, there's a food inside. Maybe there's a chicken, there's a milk, there are a number of beers. No. What is the temperature? Whatever I say silly is just to motivate. Just don't get offended or something. Okay. So there are 200 beers inside. Then what is the temperature inside the refrigerator? What is the temperature in your refrigerator in general in SI unit? About 3 degrees Celsius. Of course, the refrigerator in your house is set Fahrenheit, right? So about 3 degrees Celsius. Then what about outside of the refrigerator? Where do you place your refrigerator? Restroom? Kitchen, right? So what is the temperature in the kitchen? Room temperature. What is the room temperature in general? 20 degrees Celsius. About 20 degrees Celsius in thermodynamics. So outside is 20 degrees Celsius. So what's going to happen thermodynamically? There's a heat transfer based on the second law of thermodynamics. There's a heat transfer from outside to inside. Then what happened to your food and what happened to your beer? This temperature goes up, right? So to maintain 3 degrees Celsius, what we need to do is we need to make a heat transfer from 3 degrees Celsius to 20 degrees Celsius. So there's a heat transfer. So this is what happens in your refrigerator. We have a heat transfer from 3 degrees Celsius to 20 degrees Celsius. Is it possible? Based on the second law of thermodynamics, heat transfers from a higher temperature to lower temperature But when you look at a refrigerator, heat transfer occurs from a lower temperature to higher temperature to maintain inside at low temperature, right? This violates the second law of thermodynamics. So is it okay? No, second law is a fundamental law. You cannot violate that. So when I say heat transfer from 3 degrees Celsius to 20 degrees Celsius, this is not actually happens in the refrigerator. Then how can we remove heat from inside the refrigerator to outside? Huh? Open the refrigerator. Then there's a hot air outside. So heat goes in. So how you remove heat from inside the refrigerator to outside? If there's a heat transfer occurs this way, it's going to violate the second law. This is where we use refrigerant. Have you heard about freon gas? That's one of very famous refrigerant we used a long time ago. Some old houses, we still use them, but it is banned to use. Why is that? Because it destroys one of the layer on there, right, that protect our skin from skin cancer, right? This refrigerant is going to work in a refrigerator. So I'm going to look at this refrigerator from a side view. So if you use a side view, this is a refrigerator, and there's a door on the right-hand side. And if you look at the back of the refrigerator, you will see, you may remember there are lots of, the small tubes on the back of the refrigerator. Do you remember that? Is the same refrigerator you buy from Home Depot or Lowe's these days? Of course, if you go out there these days, they're brand new ones, so they're completely covered. But when you remember the old days, like 20 years ago, the back of the refrigerator, you'll see a lot of tubings. When you touch that, is it hot or cold? Right? Inside the tube, we have a refrigerator, a refrigerant, like a freon gas. So we are going to, I'm going to talk about that a little bit. So this is what happens. These tubes goes into the refrigerator and flowing through and then comes out. So it's a closed system. It's going to be run through the refrigerator and then comes back. It continuously, the flow through, circulate in the system. But when you look at the refrigerator in your house, sometimes you hear a sound, like a wing or something, right? Sometimes you don't. The noise, the sound is coming from a device called compressor. So there's a compressor usually at the bottom of the refrigerator. So there's a compressor. And what these compressors do? Compressor pressurize a system. In other words, it increases pressure. So this compressor increase pressure. Then, if it increase pressure, if you keep running the system, the pressure is going to increase continuously, which doesn't make sense, right? If you increase pressure, you need to decrease pressure to maintain, the constant, the property, right? So there's another device on top. It's called expansion valve that drops pressure. So at one point, we increase pressure. At one point, we decrease pressure. Now, let's see, what happens. Inside the refrigerator, we have, the food, chicken and milk and everything that is about at 3 degrees Celsius. 3 degrees Celsius. And the temperature of the refrigerant flowing through inside is going to be at lower temperature than 3 degrees Celsius. Let's say it enters at minus 5 degrees Celsius. When we talk about temperature in thermodynamics, we also need to talk about pressure. I'm going to talk about that later. And the pressure value of this refrigerant at the beginning is going to be 1 atmospheric pressure. This ATM is not the ATM that you can find in a convenience store. That's an automatic teller machine that give you, the monies, right? This ATM here is a unit of pressure that is called atmospheric pressure. The pressure of the air at the sea level, if you go to the, the east coast or west coast, the pressure at the point is 1 atmospheric pressure. Then we have a food at 3 degrees Celsius. Refrigerant is at minus 5 degrees Celsius. What happens? Due to the second law of thermodynamics, heat transfers from higher temperature to lower temperature. So there's a heat transfer in this direction. From the food to the refrigerant. Then what happens? The refrigerant is receiving heat from the food, so its temperature goes up. At the beginning, it was minus 5. Right before it enters compressor, it becomes 0 degrees Celsius, 1 ATM. Now, this 0 degrees Celsius, 1 ATM refrigerant enters this compressor. What happens in the compressor? Pressure goes up because it pressurized the system. So let's assume that the pressure went up maybe 8 times. So at the exit of this compressor, pressure is 8 atmospheric pressure, 8 times. Then what happened to the temperature? When you increase pressure, what happened to the temperature? It goes up. We are going to talk about pressure, temperature, volume relation later in chapter 2. Okay? Until that, you can assume that when you increase pressure, temperature goes up. It's like if you have this a bottle, there's air inside. If you give a pressure, what happened to its volume? Volume goes down. So when you increase pressure, volume goes down. The same thing. If you pressurize the system, temperature goes up. So when you change a property, then it affects other properties of the system. That's just one example, and we are going to discuss that later when we go to chapter 2 and 3. So because of this compressor, temperature also goes up from 0 degrees Celsius to, let's say, approximately 40 degrees Celsius. Now, this 40 degrees Celsius refrigerant flowing through the pipes in the back of the refrigerator. That's why when you touch the back of the refrigerator, it's usually hot. The new refrigerators, you don't see those pipes in the back. If you touch the, the surface, it's going to be hot because there is, the small pipes, embedded in the surface. So this 40 degrees Celsius is greater than the room temperature in the kitchen. So what happens? Heat transfer from here to the outside. So there's a heat transfer. Then after this heat transfer, what happened to the temperature of the refrigerant? Yeah, it should go down. If it stays the same, you remember the idea about having the coffee and the cup at the same temperature, then there is no heat transfer. When there's a heat transfer, means that temperature goes down. So from 40, it goes down to, let's say, 25 and 8 atmospheric pressure. Then one more question. Can this temperature go below 20 degrees Celsius? No, because if it goes below 20 degrees Celsius, then the heat transfer direction goes the opposite, which is not possible. So when there's a heat transfer, when I have this hot coffee, let's assume that it's coffee, 90 degrees Celsius, put it here in this classroom, maintain that 20 degrees Celsius. And I forgot to, grab this one, when after this class. And then tomorrow, I see the cup again. What is the temperature inside the coffee? Room temperature, 20 degrees Celsius. That's the lowest possible temperature it can go down. Because it goes lower temperature, that means that there's a heat transfer from the air to the coffee. So eventually the final temperature is going to be when you have a thermal equilibrium, which means that the temperature of the coffee is the same as the temperature of the air. So the lowest possible temperature is going to be 20. Then it's 25 degrees Celsius, 8 atmospheric pressure. Now it passes through this expansion valve. Pressure drops from 8 atmospheric pressure down to 1 atmospheric pressure. When you decrease pressure, what happened to its temperature? It drops too. The same as when you pressurize the system, volume goes down. When you depress it, then volume goes up. The same thing also happens between pressure and temperature. So we are going to talk about pressure-volume relation, volume temperature, temperature pressure later when we go to chapter 4 and chapter 2. Insulated water bottle. So technically, if you have a perfect insulator, then there's no temperature change. But in reality, the temperature drops and temperature changes. Temperature getting close to the temperature outside because there is a heat transfer. Either way, depending on the temperature, which temperature is greater than the other. Of course, you have an insulation, so the amount of heat transfer is less than without insulation. But still, you have, the energy loss, even though you have insulation. It's just a matter of, the degree of insulation. The more insulation, you decrease the, the heat transfer. Then, when you decrease pressure, the temperature goes down from 25 to -5 and then goes into the refrigerator so it can absorb heat from the food inside. So in overall, it looks like heat transfer from 3 degrees Celsius to 20 degrees Celsius, which looks like violating the second law. In reality, it is not. It's a two-stage heat transfer from 3 degrees Celsius to -5, from 40 degrees Celsius to 20. But in overall, if you don't, look at the inside, it looks like, the heat transfer from 3 to 20. So it doesn't violate the second law. Of course, when we go to chapter 5, we are going to study refrigeration system, in more details. We can, study that later. Okay. Any question up to here? It's too fast or too slow? Good. Okay. Properties of a system, while we are studying, the thermodynamics, one of the goals is going to be determine a property of a system. Property is any characteristic of a system. So when I say that there's a hot coffee inside, what do you say? Okay, the temperature of the coffee is going to be maybe 90 degrees Celsius. The temperature of the coffee is a property of the coffee. Temperature, pressure, energy, volume, mass, anything is going to be a property. So in thermodynamics, by solving a thermodynamics problem, what we are going to do is that we are going to determine a property of a system. By doing so, we can, to solve thermodynamics problem. And there are many, many properties, but there are 4 main properties in thermodynamics. They are pressure, temperature, volume, and mass. If you have a closed system, usually mass is constant. So if you don't consider mass, there are only 3 properties that play, at the same time. They are pressure, volume, and temperature. So let's talk about that. There are pressure, volume, and temperature. So they are all dependent. They are all depend on the others. So let me ask a question. If I change the pressure, what happened to the volume? If I increase the pressure of the air in this bottle, what happened to the volume? decreases. So if I say, the increasing pressure decreases volume, is it right or wrong? Sounds right, however, it is not, because we have no idea about pressure. What about I'm pressurizing the system, I'm also, heating the air, then the volume can go up, depending on, the degree of the pressure change and the temperature change. So increasing pressure will increase or decrease the volume depends on temperature. So there are three properties, three variables are playing at the same time. So we cannot just simply say pressure affects volume in this way or pressure affects the temperature in this way. And to understand this phenomenon easily, what we do is that we make one property constant. So if I, assume that temperature doesn't change, which is this case. The temperature of the air, what is the temperature of the air? The same as the air outside. Unless you heat it, unless you put it in the refrigerator, the temperature almost stay the same. Then if you pressurize the system, then volume goes down. So if you make this temperature constant, then increasing pressure decrease the volume. And decreasing pressure increase the volume. That is called constant temperature process. What about you maintain pressure constant? So if you say pressure is constant, now we are talking about this blue. So red means constant temperature process. When pressure goes up, volume goes down. Pressure goes down, volume goes up. Now the second one, when pressure is constant, if you increase temperature, what happened to the volume? Increases. If you decrease temperature, volume decreases, right? Finally, I'm going to assume that, the constant volume process. When pressure goes up, what happens to the temperature? It goes up. When you decrease pressure, temperature goes down. So when you want to talk about pressure, volume, temperature relations, the easiest way to do is that maintain one property constant and look at the other. So usually we have three, processes. One is constant pressure process, looking at the other two, constant volume process, looking at the other two, constant temperature process, looking at the other two. Okay, so that's how we study thermodynamics. That's how we simplify thermodynamics problems. There are intensive properties and extensive properties. Intensive properties mean those that are independent of the mass, like temperature in this classroom. No, regardless of the mass of the system, regardless of the weight of your system, like how much you weigh. Some people are the 50 pounds, some people are not 50 pounds, 150. 50 doesn't make sense. Or some people are 200 pounds, 250 pounds. Everyone has the same the body temperature. So the temperature is independent of mass. Pressure is also independent of the mass. So today, the atmospheric pressure is 1 atmospheric pressure. So if I eat a lot and become, twice heavy as me, then it changes the pressure? No, the atmospheric pressure remains constant. So pressure is also independent of the mass. So those are intensive properties. However, there's also extensive properties, those whose values depending on the size of the system, like total mass. If you eat more, you gain weight. If you eat more, you gain volume. So volume, mass, momentum, energy, those are extensive properties. So now the question, now there's a problem. If you want to solve a governing equation in thermodynamics, if you have a intensive properties, extensive properties together, it's going to be complicated. So you want to use only extensive properties or only intensive properties. Because of dimensional homogeneity. The dimensions of extensive properties and the dimension of intensive property, they are not the same. But if you use a governing equation, if you solve any equation, they should meet dimensional homogeneity. That means that you only use extensive properties or intensive properties. And then how can you make temperature into an extensive property? Multiply by mass. What is the physical meaning of temperature times mass? There is no physical meaning. So converting all the properties in an equation into an extensive properties doesn't make sense. So we prefer using only intensive properties. Then what about the mass? What about volume? What about momentum and energy? You can simply divide them by mass. That is called specific property. Specific volume, volume divided by mass. Specific energy, energy divided by mass. Specific enthalpy, enthalpy divided by mass. So you can simply, convert extensive properties into intensive properties. Those who were extensive properties became intensive property by divided by mass are called specific properties. So when we use a governing equation in general in thermodynamics, we use only intensive properties and specific properties. And if you know the actual numbers at the end, you can simply multiply by mass at the end of the calculation. Okay? So don't get confused between intensive properties, extensive properties, and specific properties. We're going to talk about that more, on Thursday because it's out of time, right? Running out of time. Does it end 3:15 or 3:30? Okay, so it's 2 minutes over. So, okay, that's all. Thank you.